Yeah, let me just like look for some examples real quick. But before I do that, I guess I can just tell you about the different sort of okay, so, like applications of different levels of derivatives, I guess is what you could say. So when we're dealing with just like the first derivative of a function, that's telling us sort of like where the original function is increasing and decreasing, right? Or is like going higher or going lower, right?
Yeah.
Because like when we're dealing with like some normal function and it has some upward slope like this, then that's gonna have that value, then like the slope here or something, that's gonna go to like a positive value.
Yeah.
Right? So the cool thing about the second derivative of x is that helps us find concavity. I can spell it right. Concavity. All right. So what I mean by that is when the second derivative of some function f of x is positive. I don't have a good way to say that. Okay, yeah. When the second derivative of some function f of x is positive, then that means that f of x is concave up.
Okay, and then I'm assuming when it's negative, it's concave down.
Yeah. Down, yeah. So similar to how when f prime of x positive, f of x increasing, and negative, it's x decreasing. Yeah?
Mm-hmm.
That makes sense?
Yeah.
So instead of sort of going through some function like, I don't know, so say you have some function f of x like this,
Mm-hmm.
And you want to find where it's concave up and concave down, right?
Yeah.
So you need to first find the first derivative because you're looking for the second derivative, right? Because that's what tells you what if it's concave up or concave down, right? So first derivative is what? 12x squared?
12x to the squared, or second, and then 4x plus 1.
Yeah, exactly. Can you
And then the
this?
second derivative would just be 24x minus 4.
Yeah. Yeah, exactly. So given this, we want to find the points, the input values of x, where this function is going from being positive to being negative, like its output values, right? Because I can just tell you right now that this function, I mean, it's linear, right? It only got like x is just changing, and then that's all it's doing, right? It's just a linear function. So it's doing something like this, right?
Yeah.
So we want to find this point because right here is where we'll this x value is at the same point for f of x, where the function is going like this or like I don't know, like the other way around. Like
Yeah.
Yeah, you know what I mean. It's like changing because this is positive, this is negative.
Okay.
So we just need to find its x value. So how do we find that?
You subtract, or you add 4, and then you divide by 24.
So what do we change f? Do we change this to anything?
Oh, 0, sorry.
Yeah.
So would it be 1 over 6?
Like probably. So yeah. So 1 over 6 equals x. Great. So now we have to do that little like table of values thing, right?
Oh God.
With the like the whole number line, right?
Mm-hmm.
Okay. So what do we do? We minus x, or you can just do like 24 x minus 4. I don't know if he's like showed you a good way to do this. This is how I learned. So we have this x value, 1, 6. And we want to see if it's sort of like, if values greater than it are positive, which I mean, you can kind of tell like this slope is going up all the time, so it's like not there.
Yeah.
But you still should like plug it in just in case, right?
Mm-hmm.
So what should I plug in on to get like either side of this sort of?
Could you just do like 1 and -1?
Yeah, 1 and -1 works great. So let's plug in 1 for on this side. We plug in 24, 1 minus 1, 24 minus 1, 3, and that's positive. So, okay. Sorry.
And so then the other side would be -25.
Yeah. So 24, -1, minus 1, 4 minus 1. Yeah, -25. Yeah. So negative.
Yeah.
Great. So this basically tells us right away that from negative infinity to 1/6, we are concave down. Right? And then from what, 1/6, almost 1/6 to infinity, that's not a 6. Okay. We are concave up. That makes sense?
Yeah.
And I mean, if I like, I don't have to plug this into like Desmos or something, but you could tell pretty easily that, this is what it would look like. So I don't know how it would go. So you're trying to like that 1/6, it would turn to be it's probably like something like this, right? Because this is down, it's kind of up. Oh, you can't see that. This is really true. So like if this is 1/6, it's something like this. So this is clearly concave down, like it's sort of like got that maximum right here.
Okay, yeah. And then if it's a minimum, it's concaving up.
Yeah. Or if it's sort of like doing this thing, like it's making a U almost. And it's like it looks as if this looks like it's a valley, then it's like concave up. And then if it's more of like this hill shape, it's concave down. And this point in the center, do you know what that's called?
Oh. Not critical point, but
I think it is technically a critical point, but there's another word
it started with an I.
yeah.
I don't remember what it was, but I know it was like I don't remember, but I know it started with an I.
It's called an inflection point. You're close. But yeah, no, that's great. That's great. So you were very close. So yeah, so that's just a pretty just general sort of like overview of concavity. And that, I mean, just this very simple sort of stepwise process of thinking about, okay, if I want to tell if the function is increasing and decreasing, or like where it's increasing and decreasing from, then I only need to use the first derivative. Whereas if I'm trying to find the concavity to see where the function is concave up or where the function is concave down, then I should use the second derivative, right?
Mm-hmm.
And you basically solve them the exact same way. It's just one is only the first derivative, the other one's the second derivative, because they both involve plugging in the 0 and then doing this like number line thing, right?
Yeah. Okay, that makes sense.
Yeah. Do you understand? Okay, cool. Yeah, and I went over in the last session, I also went over like an example with velocity and acceleration, how those and like what speeding up means and that kind of thing. So I recommend that like if you're sort of having trouble or if you sort of want some review with all this like first derivative stuff versus the second derivative stuff, like I definitely recommend checking out that one. Just because we went through a few examples. So
Okay, sounds
that work. Cool. Are there any other specific things you sort of?
No, I just like honestly, I have not really understood what he's like said this week.
Okay. So, what did he go over on Monday? Because I was gonna do what he said what he went over yesterday, Oh wait, Monday we got out early, didn't we?
No, Monday was the best day ever. The
Oh
Zoom
yeah,
was out.
he let us out early. Okay, cool. I remember that because I was kind of hyped too. I was like, nice.
Oh my god, I was like half asleep, like watching it, and then it stopped working, and then like I just like rested my eyes for a little, and I opened them, and I looked at the chat, and he's like, "You guys are free to go," and I was so excited.
Yeah, I know how you feel. Yeah, that was nice. Okay, wait, I'm just like looking through my notes.
No, we could go over what he did yesterday too, because I was lost there as well.
But yeah. So the stuff that you went over yesterday is actually, at least from what I remember, was definitely one of the harder topics, and one of the topics that most of my friends struggled with, and one of the things that I had a bit of trouble with at first, and then once you sort of like understand how to work those problems, it sort of just like figures itself out. So I'm like 99% sure this is what you went over. It's called like related rates. I don't know if that rings a bell at all.
I think so.
Okay. I don't know what section it is on your textbook. I can like check really quickly.
I think it was like 4.5 maybe. I'm not positive.
Okay. Yeah, because it's definitely in there. It looks like it is 4.1. So he skipped around a little bit because linear approximations, which we did before this, is 4.2 and some other stuff. So, okay, that's fine. So the idea behind related rates is basically like taking like word problems and then looking at the values that they give you in the problem, corresponding those values to like variables basically in different like formulas that you can sort of like create and that you will recognize. And I'll show you this. And then you basically just like solve for stuff. I think this is one of those like types of problems in calc that's like honestly at its core not that difficult, but when people aren't sort of like shown step by step the process of it, it can be a bit more challenging. So I think I'm just gonna like take you through one of the examples, very similar to what he did, and then hopefully I can sort of connect some dots for you. Does that sound okay? Yeah. Okay. Cool.
Yeah, sounds good.
So let's just say we have like a rectangle with length L.
No, yeah. This is what he's doing. Then he's like cutting out the corners.
Yeah. So like cutting out corners is like one way to do it. It's all like sort of the same steps, except this time I'm not going to cut out the corners, and I'm just going to work with area instead of him cutting out the corners and then doing a volume thing. Very similar process, very similar like idea. It's just slightly different, I guess. And honestly, mine's probably going to be a little bit simpler, if that makes sense.
I'd rather it be simpler.
Okay, cool. Yeah, that's what our example is going to be. Okay, so let's say that the length of the rectangle is L increasing by 0.8 centimeters a second. Okay. And that the width is decreasing by negative, or I guess by 0.5 centimeters a second. All right. Okay. So what I want to know is how fast the area of this rectangle is changing when the length is 20 centimeters and the width is 10. So area change. This is my symbol for change right now. Okay. So these are like our givens. Now, in any related rates problem, you should always write these out very explicitly. And then once you sort of have an equation to model the situation and you like do your derivative and stuff, try to take your givens and associate them with variables that you have found through your formulas, basically. So right now, what are we trying to sort of like model right here? We're trying to find the area of this rectangle, right?
Mm-hmm.
What what's like a formula that you know that can maybe like show us
Length times width.
length times width? Yeah, exactly. So A equals L times W, right? Okay.
Yes, 200, right?
What'd you say?
It'd be 200 at the start, right?
Uh, yeah. So we're getting there. We're getting there. But yeah. So if you do just so yes, actually yeah. So if you do A equals 20 times 10, then you'll get 100 centimeters squared, right? So that's the area at this specific moment. That's 200. Sorry. But what we're trying to find is how fast the area is changing, given that the length and width are changing at these speeds when it's at this size. Does that make sense?
Yeah.
Okay. So when we're dealing with something that's changing, such as the area that's changing, how do you think we could like write a formula or like model that sort of idea?
X and Y.
I
I have
mean,
no idea.
you could think about it in terms of X and Y, but think about it in length and width is a little bit better. So how we're gonna do it is pretend like basically the main idea I'm trying to get at is you want to take the derivative of this function as if this is sort of like your output in a sense, and these are your two inputs. And then when you take the derivative of it, you basically can tell how this is changing because you're taking the derivative with respect to time. Sorry if that doesn't. So basically what I'm saying is like this, when you plug these 20 and 10 values in, you're basically saying like, okay, I'm plugging this 20 value and this 10 value in as like basically values of t so that when I do this, no, that's wrong. How should I say this? Yeah, I don't want to think conceptually because I'm really bad at explaining that thing. So what we're just going to do is we're just going to take the derivative of this function, of this sort of equation that we have with respect to t, and then we're going to have some variables left over that we'll be able to sort of associate with these givens that we have over here. All right, and then maybe you can then hopefully you'll be able to sort of like tell what I'm sort of talking about. Okay, so we do the derivative. This is like the derivative.
Yeah.
Of a derivative. So this is like taking the area, the derivative of the area
Is equal
with
to
respect to t. So it's basically saying like, okay, this is like showing us how it's changing. And same with this. How it's changing over time, like the rate of change, right? Because that's what the derivative function is. It's telling us the rate of change of the original function, which is this. So how should I like simplify either of these sides?
like d over dt of 200.
So this is just sort of like telling us, okay, the area is here, so we don't really need to worry about this.
Okay.
I'm just talking about like these two parts.
Could be like d over dt of 0.8 times point. I have no idea.
So try to just keep it in terms of the variables right now. So on the left side, I'm just going to sort of say like, okay, all we have right here is just the derivative of whatever this is, right? Okay.
And then times dLw over dt.
Can you say that again?
Like dLw over dt.
So.
Or could you do like dl times dw over dt?
So the thing that is we need to notice here is that we're actually going to be using the product rule because of how these are sort of both variables in a sense. Does that make sense?
Yeah.
Sorry if that like I know it may seem like a bit of like like strange at first, but we kind of need to think of these each as like input values, whereas this is sort of like our output. But we can still take the derivative of each of them. So we need to use the product rule over here. So to do that, so pretend each of these are sort of their own like separate little functions, right? So to do that, we do like the derivative of the first times the second plus the first times the derivative of the second, right?
Yeah.
So, yeah.
Times.
Right?
Yeah.
Okay, so now we have this variable that sort of tells us, okay, this is like how the area is changing, right? We have this. What does this tell us?
It tells us like how each side is changing, like the length side and the width side.
Yeah. So this is the length side and this is the width side, right?
Yeah.
And this is just like any specific instance of the actual width. And this is any specific instance of the actual length, right? There's like 10, 20, 10 values, right? So if we were to write these values here, which of these would correspond to which of these?
So for the length, for DL, would you put 0.8?
Yeah.
And then would it be times 10?
Let's can we, instead of like so I like where you're going. Let's just try to like write all these values out so that we have sort of like something to
Okay, and then would DW be negative 0.5 because it's decreasing?
Yes. Yeah. Um, you don't really need units, but I'm just including it anyway. Okay, so what are the rest of this?
And then DA would be X, right?
What do you mean?
Because you don't know what the derivative of the area is yet, how it's changing.
Yeah, that's true. So what we're trying to remember that in the original problem, I didn't really write this down anywhere, that we're trying to find how the area is changing at this specific point, right?
Yes.
So in general, what we're trying to find is this value dA by dt. Because when you plug in these two values alongside these sort of rates of change values, they're going to sort of like combine and then they'll tell us how it's changing, right? So this is what we're actually looking for. This is what we're trying to find, okay?
Mm-hmm.
And you'll notice that we have 4 values given to us and 4 different variables, right? So what are the last 2 variables that we can sort of like plug in for here?
Oh God. I just don't know what A would be.
So we don't need to know A.
Okay, then, well,
Yes,
W,
because, so W is what?
could it be 10? So that's
Yeah,
what we're
10.
given. And then L would be 20.
Exactly. Yeah, so we don't need A because, well, one, we found what A is up here, right?
Okay.
I know what A is like at this specific time, but we're not looking for what the area is. We're more looking for, how should I say? We're looking for the rate of change of the area at this specific point. Like how is it being changed? All right, given that the length and width are changing like this. So we're trying to sort of relate how the length and width are changing to how the area is changing at the same time.
Yeah. Okay.
Yeah. Okay. So plugging in, because we have a value for pretty much all of these things, right?
Mm-hmm.
All we have left right now is just to sort of like simplify, which is good. So we're going to do our 0.8 times our width, right? Okay.
Yeah.
Plus, well, minus actually, right? Because this is negative. Minus our 0.5 times 20. This is what? This is it's going to give us 8. Minus, what will this give us?
10.
10. Yeah. -2. Okay. So that means that our dA by dt is -2 centimeters per second. So what can you tell me about how the area is changing.
The area is decreasing by -2 centimeters per second.
Yeah, at this specific moment where, at this specific instant where the length is 20 centimeters and the width is 10 centimeters, and this is how the length and width are changing. Yeah, exactly. Okay, cool.
Is that it?
So, yeah. So that's it to the problem.
That's not like terrible.
Yeah, I know. Like it's really not that bad. So
I thought there was gonna be more.
no, I know. It's like it's pretty self-explanatory. I feel like. It's just the important thing is that you guys are going to be to recognize that what you guys are going to be dealing with are they're going to be giving you shapes that you should know, like the areas and the equations for like the area or like the perimeters for. I think on our final or maybe our midterm for this like part of the course, they gave us one with a circle, and I remember a ton of people. I know a ton of people are really pissed about it, but the area of a circle is just pi r squared, right?
Yeah.
And like, I mean, you can take the derivative of that, right?
Yeah, wasn't it just 2 pi r?
And I mean, I don't know if you noticed this, but do you recognize that from anything either?
Oh, I know it's another circle thing, but I don't diameter, right?
It's the perimeter. It's the circumference. It's the circumference, right? Which is just like another cool thing. I remember like in one of my Calc 3 classes, we like proved that this is what it is. But like that's sort of like besides the point. But I mean, it was literally just like, oh, you also have to do like
Ugh.
yeah. So I mean, I think there might have been like a chain rule thing or something with like there's like an R thing. I'm not sure. There's probably like another like dr by dt or something. You guys have to take the derivative like the inside or whatever. Um, and then they would tell you like, okay, like at this specific radius, for the radius changing at this much, how is the area of the circle changing, or something like that. And all you would have to do is just try to plug in, right? And then
So
you kind of get
probably,
it. What?
for that case, you would just plug in like the derivative of the radius and multiply it times the original radius.
Yeah. So by original radius, it's important to know that it's like the radius that they give you. Like it's the radius like where you want to find the rate of change of the area at a specific point of time, or when the radius is at a specific length, and that's the radius that you plug in.
No, yeah. So if it was like the radius is decreasing at like 0.3 and it's like started out at 5, would it be like 2 pi 0.3 times 5?
It started out at 5.
Yeah.
Yeah. So the radius would be that 5, like r would be 5, and this would be 0.3 because it's
Yeah.
0.3. Yeah. Or the negative 0.3. Yeah, exactly. So I think, and if you're just given like if you wanted to know how the circumference was changing, for example, if you have 2 pi r and you're told to find how the circumference was changing, I'm like 99% sure this is right, where it's literally just well,
yeah.
I think it's just it's probably like all the same, because I think it's just dr by dt, and then it doesn't matter how long the radius is. But I mean, that doesn't matter. I wait to check if those are right. What I'm just saying right now.
No, but like it's making like sense.
Yeah, which is good. So I'm just like checking other things because I don't want to like teach you something and then it'd be wrong or something. Okay, yeah. So I just like would watch out for those kinds of problems. And I have like another related range problem that sort of is a little bit harder to find these input values, because they're not always going to just give you like the length, the width, and how they're changing. They might give you only like how they're changing and then the length, and then somehow you have to find the width using some math thing. And that's normally what you're going to be doing with like triangles or something. Just because you can use like the Pythagorean theorem in different ways, right?
Yeah.
Like do different stuff. Yeah. So okay, cool. So do you want me to do like another one of these problems with like another shape?
Sure.
Let's think. Okay. Okay, let's say a person, I guess like we can say like a woman starts walking like north. It's like you can say person one, P1, walks north. What is it? 8 miles per hour at t equals 0.
Okay.
Okay, and then P2 heads east at 5 miles per hour at t equals 0 seconds. Or 0 minutes, sorry. 0 min. T equals 15 min. Okay.
Okay.
So what we want to find is distance between P1, P2, or rate of change of distance. Rate of change of distance between P1, P2 at t equals 45 min. All right.
Yeah.
So this is sort of the problem. So the first thing I want to ask is how would you find not the rate of change, but just the distance between them alone?
Pythagorean theorem.
Yeah. So you can model this sort of like a triangle, right?
Yeah, that's
Or like this is like that distance. So this is your 8 miles per hour. This is your 5. Right? So how would we find this distance? Let's say this distance is distance z. This is
Would
we
you
can make
do
this y.
64 or 8 squared plus 25 squared equals the distance squared, so c squared.
So let's think about what each of these mean, right? Because what we're trying to do right now is we're trying to plug in values of distances, right? Because x is a distance, y is a distance, z is a distance. So we're planning to plug in x, a distance x, and a distance y to then solve for some distance z, right?
Yeah.
But all we're given are moments in time and speeds, right? Velocities, in a sense, right?
Yeah.
So we need to sort of somehow use this information that we've been given, this speed of 8 miles per hour, the speed of 5 miles per hour, along with these intervals of time, to see how far each person walked in that amount of time, and then we can sort of like pinpoint where they are and then find the distance between them, right? So how do I? We're not trying to do any derivatives yet. We're just trying to find what z is at this moment. So basically what I'm trying to ask is like how far has person 1 walked
8 miles
over 45 minutes going at 8 miles per hour?
Zero.
So they're walking north at 8 miles per hour, and they've walked for 45 minutes.
Oh, you would divide it, so it's 6.
Yeah, right? It's just 6.
Yeah.
Cool. And there's like some conversion thing, but I just think of this as being like 3/4 of an hour, and then you can just
Yeah, that's how I just thought, like 3/4 of 8.
Y equals 6. Okay, cool. So what's x then?
15.
How?
Or no, oops, so it's 3/4 of 5. Hold on, let me multiply that.
Well, Are you sure it's 3/4?
Isn't it how far they've walked?
And how long?
They
We're only
walked-
looking at person 2 right now.
Yeah, so they walked for 5 miles an hour at 15 minutes. Oh, so it'd be a fourth of 5?
Well, it's just this is 30 minutes, right?
Yeah. Oh, duh. Okay. So half of 2.5.
Yeah, yeah. So this is just 2.5. Great. Okay, and then this is where we can use the right triangle stuff, right? So we got x squared, y squared equals z squared, right? So we can just plug in 2.5 squared plus 6 squared, all plus 6 equals z squared, and then I'll just like give it.
Yeah.
So root 42.25 z. Cool. Good stuff.
Is that the answer?
No.
Okay.
So this is just finding out what the distance is between these two people at t equals 45 minutes, right?
Yeah.
What we're looking for is the rate of change of the distance between the two people, right? Similar to how we found the area as these lengths and widths had their specific, as the length and width had their specific values, but we were instead just trying to find the rate of change of the area, not just the area, right?
Yes.
So there's sort of like that difference there. Okay. So how can we use this idea of modeling P2, P1? We have this formula basically that tells us what the how should I say? We have this formula that tells us what the sort of distances are between all of them, but we're just trying to find the rate of change, right? We're only trying to find the rate of change. Whereas similar to here, like we were just trying to find the rate of change given these distances to compute some area, right? So what did we do last problem that we can probably do to this?
Let's find the rate of change. So we have the distance between the two. Shit. Derivatives, maybe?
Okay. So what do I take the derivative of? It's already written on the page.
The Pythagorean theorem.
Yeah. Exactly. Okay. So this uses some weird ass like implicit differentiation stuff, sort of.
Mm-hmm.
Sort of I was getting at last time with this down here, where you take the derivative of it, and you not only do this, but you also multiply by like dr over dt, right?
Yeah.
Very similar. So if I was trying to do this like by r, I'm trying to do just 2 pi and then dr dt. I'm like pretty sure that. Sorry. That'd be 2 pi or dr dt. I'm like pretty sure. I'm pretty sure that dr, yeah.
Yeah.
Whatever. Cool. So for here, we don't need to do any like fancy product rule and stuff. We just kind of like derive simply. So I can just bring that 2 down for the 2x, then multiply, sort of like implicit differentiation. You multiply by the derivative of x, right?
Right.
Similar, same with y. Same with z dt. Okay, cool. So we got this funky looking thing with all these sort of parts. I'm gonna like highlight them in different colors so you can sort of like see them. Okay. So what are we trying to solve for in this equation?
z, the rate of change,
So which part?
the derivative of z.
Yeah, so we're trying to solve for this, right? Okay. So what can we plug into here?
So you would have 2 times 2.5
Times what?
the derivative 8. No.
So remember, this is x is this right one for person 2,
Yeah.
right?
Oh, it'd be maybe 5.
Yeah. Plus
Oh, plus 2 times 6 times 0. Or no, times 8 times 8.
6 times 8. Yeah. Okay.
And then equals 2 times root 42.25 times 45. No, that doesn't equal. Maybe just times t.
Why t? Why not? Why not just? We're trying to solve for this, right?
Yeah, times derivative, whatever. That was just what I'm saying, like a variable.
Yeah. Exactly. Okay.
And then you have
And then you
5
choose.
5, so 25.
Yeah.
Plus 48 times 2. Oh God. I think that's 96.
It is.
And then whatever that is.
Yeah. 5 times dt.
And then
And
you
then
divide by the root thing.
yeah. 2.25. Right.
Mm-hmm.
And it sort of simplifies. That's it.
Damn.
So, what have we found?
We found the rate of change at t equals 45 minutes.
Between what?
What?
Of what? What did we find the rate of change of?
Of like the miles per hour.
But like, what does it like represent in this?
Oh, the distance between x and y.
Yeah, the distance between the two people, right?
Right.
Yeah. Cool. So yeah, so that's like sort of just like, I mean, that's just a good example of sort of like getting through one of these. What do you think?
I don't love it, but I don't hate it.
Yeah, it's not that bad in hindsight, I don't think. I mean, it's just sort of like saying, okay, we have these values which we correlated to x, right? So I can just sort of like highlight that right here. Yeah, these other values are correlated to y.
It's just kind of hard figuring out like what goes where.
Mm-hmm. I know what you mean. And that's the challenge with these problems. Once you have all the parts and pieces and you know how to plug it in properly, then it's pretty easy. I mean, it's basically just normal algebra.
Yeah.
But it's this idea of like taking some kind of situation, modeling it as some kind of shape or something, and then fixing some kind of formula that you know you can put, that you can sort of like show the shape as, and then going from there. That's where the challenge comes from. So normally when you're given a kind of problem like this, it's going to be some kind of like, oh, you have the volume of a box that you're trying to like maximize and minimize. And that's also sort of what the Bradshaw went over. And honestly, you know what? I don't know if you guys have gotten to this stuff yet, because now that I think about it, he was doing more of like trying to like maximize the volume of things, which is similar, but it's not exactly the same. Because when he does like the maximizing of volume and stuff, it's basically just like, okay, it's honestly like this stuff, but sort of like a step down. It's a little bit simpler.
Okay.
Because, I mean, you say you have like some box, and then you like fold the sides as like some length x. It's basically the same thing that we did here, where you model the area, but in that case, volume, based upon like those lengths, right? And then you just find a couple derivatives, set it equal to 0, see where the maximums and minimums are, and then if you find some like maximum of that volume, then I mean that's sort of like all you have to do. So I'd say even this is more difficult than what he did in class yesterday. So you might see this tomorrow. So I'm sorry for like jumping ahead a little bit.
No, I'd rather like learn how to do the hard stuff now, so I can like kind of follow it tomorrow than like, I don't know if that makes sense, but like then like
Oh yeah, I get that.
on the easy stuff, then be like shell shocked tomorrow.
Mm-hmm. I know what you mean. Yeah, for sure. For sure. Okay. Okay. So I still have like 12 minutes. I'm trying to. Oh, good. Okay. Sorry, I'm just like sort of looking through
No, you're
future things. Oh, so maybe he skipped to like optimization or something, which is interesting.
I feel like I've heard that word.
Yeah, I think he skipped ahead to optimization because that's when like you're trying to like find the maximum volume or maximum perimeter or like something like that for some kind of situation, and you only have to deal with the first derivative in that case. Like, I don't know if in my notes, I literally have written down like optimization, you just think first derivative instantly.
Yeah.
So that's probably something I can go over, I guess, in the future because
Yeah.
I guess I wasn't paying attention. That's fine. Can I take you through some just like the notes just to sort of like show I have just sort of like hone in these like this idea of like concavity and then increasing stuff.
Sure.
Cool. Along with like the number line thing, just because I know that's sort of like a big, very important. So this is like my notes from when I took it in class.
Wow.
So I think what our professor did was like he drew out this sort of like graph thing, and then drew out these points 2 and 4 at different points. So we can see here that like f is increasing. And this is where that derivative of f is greater than 0, right? That's when it's positive. That's where f is clearly decreasing. We have a negative slope. It's where that derivative is less than 0, negative. Same, and then again, like f increasing again, right?
Mm-hmm.
Okay. So going sort of over here. We have this thing called like the first derivative test, which basically allows us to tell whether or not you have a maximum or a minimum at different points, right? So if you take some, how should I say? If you have some critical, oh yeah. So we say we have some critical number C of f. And by critical number, I mean it's an x value for which the derivative of the function is 0. So it's basically like when you take the derivative of f and then set it equal to 0 and then solve for x, right? Those are critical numbers, right?
Yeah.
Makes sense? So if we say our critical number was 2, and the sign to the left of it was positive, the sign to the right of it was negative, then we know it's a maximum because the slope must have been increasing and then started decreasing, right?
Mm-hmm.
Makes sense?
Yeah.
Okay. So we can do the same thing with if it's negative on the left, positive on the right, going down and then goes up. But if it's positive and positive or negative and negative, then we can't really tell, right?
Yeah.
Well, I guess you can. It's kind of like this, right? This is what normally happens because it has to hit 0 eventually. So that's why it kind of flattens out. But you'll notice that the concavity changes there, right?
Mm-hmm. Interesting.
But like, yeah, right? But that's the reason why we have this second derivative test. Because it allows us to see, what's the word? See, sort of how this is changing. So sorry, that was poorly explained. So sort of a similar graph from what we drew last time, right?
Mm-hmm.
When we have this function, when we have this, what's the word? When we have this concave up part of the function, right, which is right here, when it's before it starts to go concave down, this is more like a valley, this is more like a hill, right?
Yeah.
This is where the derivative of f is increasing, right? Because as you can see, this slope right here, it's pretty far down, but it's very negative. But then it's growing, right? As it goes like this, like the slope is getting positive. These lines are starting to point from pointing down to being pointing up, which means that the slope of this function is changing. And it's increasing, which means that our derivative, the second derivative, or the derivative of just that first derivative is positive.
Yes.
Yeah, because if the slope of the slopes, I guess, if that's kind of a bad way to explain it. But yeah, like you always want to just think about it as like your rate of change in whatever function you're living in. If it's like if it's like increasing, then the derivative at that same point is positive. And then if it's decreasing, it's going to be negative because it's all about like the slopes, sort of. You always like drawing these like little like lines always sort of help me. And then we can sort of see like the opposite side of that with being down, right? So you can see that on this point right here, like from right here, this function is still increasing, right?
Yeah.
The slope is still positive, but the slope is but the slope is decreasing now, right? Because like as you can tell, like this could be like a slope of 4. This could be a slope of 2. This could be a slope of then -1. This could be a slope of like -3, -5, -13. So it's decreasing. So we can say that it's concave down, and that the second derivative is negative.
Yes.
And so doing all these things allow you to sort of like draw out points, draw out functions sort of closely when you kind of use both the first derivative test and the second derivative test sort of all together. I don't really want to take you through any of these problems just because they were going to take a while. I remember doing some of those box questions that what he did in person. Do you have any other like questions about other things about like derivatives and stuff?
No, it's just like we're getting to the point, like this unit stuff I didn't do in long calc. So it's like I'm like I actually when I don't know something, it's like not even like vaguely familiar. It's just like I don't even know what he's talking about.
Mm-hmm. Yeah, I understand. It's definitely like a lot of like complex concepts, and it's an early class, so I'm not. I
Well,
can't.
yeah, I was like thinking, I was like, I mean, it's not like I'm doing bad at this class by any means, but I'm like, I could be probably doing like 2 or 3 percentage points better if it was at the afternoon.
Yeah, like a reasonable time. I know what you mean. I can't imagine doing this super early. Like, I think I took it at like 11, or like, or maybe I was at like noon or something.
Yeah, my calc class last semester was like at 1, and it was so nice because I was like awake. I'd like had a few classes already, like I was in the groove. But like the fact that it's so early and it's my first class, and then it's like I still have 3 more after that, it just makes my day so long.
Yeah. I know how you feel. It's not like because I have Lin Alg right after this as well, so it's just like a lot of math in the morning.
I know, I cannot. Like my roommate doesn't even go anymore. She just sleeps.
That's honestly like understandable. Yeah.
No,
Okay. I'm just trying to like look at sort of this problem. I didn't really like prepare to go further than what we sort of already covered just because I didn't think we would need to. I mean, yeah, like all this stuff you can sort of if they're gonna throw something like this like chemistry stuff at you, like they're gonna basically give you all of the different values that you need to find.
Mhm.
I know this looks very complicated, but it's basically the same thing that what we did for like the length and the width, right?
That's just like giving me flashbacks to chemistry, and I
Yeah, I know, right? So we have this equation. We want to probably what? We want to find like how much is like the volume decreasing given that the volume is 600, like the pressure is just like whatever the unit is, and it's also increasing.
yeah.
So you do the derivative. I guess you can set this equal to 0. Oh, it's a constant. Okay. So since you do the derivative of constant, it can be equal to 0. Then this goes here, volume. And then it's pretty much just like you always have to remember like that idea of implicit differentiation like is there. So that's really important. Like when you do the derivative of it, it's not like a variable like x when you're doing the derivative of like x with respect to x. Like it doesn't just go away. It doesn't just become 1. You have to do it basically like represents the derivative of itself sort of. Because you're not like if you're doing like, if you have like circumference equals, I guess I'll write this on my other piece of paper. And this would be like the last thing I mentioned. You have this like circumference equals like 2 pi r. If you did this up here, but you want to do the derivative with respect to like r.
Yeah.
Which you will do in Calc 3 if you go that far. But
I will not be going to Calc 3. I hope after this class I never touch Calc again.
understandable. And then, then you have this as what your derivative is. But because we did it with respect to t down here, which you can't really see, then you still have to, you can't like get rid of it. Does that make sense?
Yeah.
Yeah. Cool. So yeah, that's all I sort of want to like go over. I'm probably gonna stop sharing and sorry, my throat is like killing me right now.
Oh no, you're fine. I've been sick like for 2 weeks, so.
Yeah, not having a good time.
All right. Thank you.
Yeah, of course. Have a good one.